Hello, wonderful people. Welcome to Cosmology Talks. Today we have Pritha Paul, who is a PhD student at Queen Mary University of London, and Chris Clarkson, who is a professor at Queen Mary. They'll be talking today about parity violation and the fact that we actually expect to observe it in the standard cosmology. Yeah, that surprised me too when I saw their paper, but they do appear to be correct, so let's let them explain themselves. Getting to the spoiler, the hint is that the key lies in relativistic redshift space distortion effects that naively one would ignore because they're subdominant. However, when the Newtonian effects are zero, subdominant stuff can become dominant and perhaps measurable if we're clever enough. This is interesting because, of course, there are a few hints nowadays of measured parity violation. And in fact, one of the most popular talks on this channel was one of those hints, in particular in the 4-point function of galaxy positions, which is also where Pritha and Chris say this effect should be. This is one of my favorite aspects of cosmology, the kind of ever more clever detective work where we go deeper and deeper, both observationally and in calculations, at what we expect. It's like a detective novel where the crime is solved by the clever detective using ever more subtle and revealing clues. And in this case, parity violation becomes that one where we think we've found some grand new thing, and then perhaps we find out we actually just misunderstood the standard model. I should say that Pritha and Chris say in their paper that the effect they've noticed in the standard model can't be the thing that people have claimed to have observed. However, I should also say I'm not sure I fully understand the reasons why. So I'm very keen to hear about that as we go. Otherwise, this could have been the leading contender to explain that. So welcome, Pritha and Chris. Do you want to start by telling us briefly about your paper?
Yes. So in our paper, we have calculated the parity odd part of the observed matter trispectrum, which is the Fourier counterpart of the 4-point correlation function.
Great. If people are thinking of this talk or your paper 6 months or a year from now, and there are only two things they remember, what would you want those two things to be?
So the intrinsic 4-point correlation function is parity invariant, but the trispectrum is observed in redshift space. And although the Newtonian approximation to the redshift space distortion is parity symmetric, the leading relativistic corrections do not respect this parity invariance. And at quality scales and beyond, these contributions can be significant and become dominant over the Newtonian parity invariant part. So when we are observing this 4-point correlation function, we should expect to detect this parity violation at large scales.
Cool. And yeah, I guess we'll put a pin in the have we already detected it or not. And I promise we'll get to that later on because I'm super curious. Cool. So why did you do this? Like, what questions were unsolved that you wanted to or needed to solve? Why were they unsolved? I mean, you've given an intro and I've given an intro about parity violation, which is very exciting, but let's go into the further details. And yeah, why was this done in 2024 and not say, 2018 or 2026?
So at large scales, the symmetries that we observe in cosmology, we usually assume the universe to be homogeneous and isotropic, which respects the translation and rotational symmetry. However, nowadays people have been looking into what about the reflection symmetry of the universe. So there has been research going on about this reflection symmetry, and people have found out that the universe may be asymmetric on these large scales. So the way that we define this asymmetry is by parity symmetry, which is a symmetry under a point reflection. So you are taking your function and doing a transformation where you go from the positive coordinate systems to the negative coordinates. So in 3D, you can think of parity violation to be simply a reflection about a plane and then followed by a 180-degree rotation about a vector which is perpendicular to the plane. So far, when focusing on parity violation, people have usually looked at the CMB, ENB polarization modes. So they have looked at the parity violating part of the CMB, and they found 2.4 sigma evidence in that parity violating part. The evidence has been refined by some other people called Eskilds and Komatsu, and they found a 3.6 sigma evidence. But recently, in 2023, Khan, Slepian, and Hu, they have found a novel proposal of using the Galaxy 4-point correlation function at late times to probe this parity asymmetry rather than using CMB polarization modes.
You always want, when some anomalous signal shows up, to find another anomalous signal that is very similar, and then you're like, okay, maybe these are related. But apparently these things are both parity violation, but very difficult to think of why they might be caused by the same thing, though. Unless both of you have an idea how that might be happening. But I guess your thing wouldn't affect birefringence, would it?
No,
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 no.
no. But yeah, so recently they have proposed using these 4 points, so whether we can actually map this parity violation going on at much larger scales. So the reason why we have to go to the 4-point correlation function and not just stick to the 2-point or the 3-point correlation function, I think the easiest way to think of it is that when you're thinking about parity violation, you're thinking about a mirror image and a rotation. So for the 2-point or the 3 points, you can perform this mirror image and rotation and still superimpose the image that you get back onto the original image for the 2-point and the 3-point function. But once you have the 4-point correlation function, if you do a mirror image and a rotation, the resulting image can't be superimposed back into your original image. So I think the best way to think of it is that you have this 4th point, which is either protruding in or protruding out of your plane. So when you do this rotation, when you do this transformation, you don't end up getting back to the same image. So you can't superimpose them on top of each other. Followed by this work, after Kahn introduced this idea, I think Phil Cox did this blind test on the CMAS catalog where they found around 2.9 sigma evidence for the detection of an odd parity 4-point correlation function. However, recently a paper came out where they thought that they underestimated the covariance and the detection went down to 1.9 sigma. But Hu et al. Did an analysis as well. They did an analysis on 2 sets of data, and they found a 3.1 sigma evidence and a 7.1 sigma evidence on the above data sets. And they did their analysis in a little bit different ways, I think. So we don't know yet whether they would find anything in their analysis.
Yeah, if anyone wants a very detailed technical dive into the differences between the analyses and the opinions, why Oliver Philcox did it one way and why Jim and Zach and Bob did it another way, because they were collaborating initially on this. So the methods are very, very similar. It's just like final analysis decisions. But at the Parity Violation from Home conference last year, there was a panel discussion that had both sides kind of discussing why they had the different analysis decisions. I mean, it's fair to say that I think Oliver is very much convinced that it is somehow systematics, and Jim and Zach and Bob are very much, well, not very much convinced, but very open to the idea that it is seeing something that is actually parity violation.
What was the reason for Oliver Philcox thinking that, or what was the essential argument?
If I can try and remember and paraphrase, there are a few very clear sticking points. One is Oliver expects that for the types of models that could produce this, you would expect it to have been seen in the CMB because the CMB has so many more modes. And although the CMB is kind of 2-dimensional, there's enough 3-dimensional information because it's a sphere rather than a flat sky, that even though that effect as you go to smaller scales makes the amplitude of the signal shrink, there are so many more modes as you go to small scales that the more modes thing dominates, and you should have seen it, and you haven't. In fact, Oliver's the one who looked for it and didn't see it. I guess Zach and Jim would counter that. Okay, maybe the models that Oliver likes aren't what caused this real signal in the universe, and if it has a scale dependence or if it doesn't have a scale dependence, I can't remember exactly, then as you go to small scales, maybe it's not there anymore. They had some argument why you might expect to see it at larger scales. And I guess your signal, I think, is such a thing that you would expect to see at larger scales.
Yes.
Yeah.
So that was why Oliver, I think, was most skeptical, because he didn't see it in the CMB. I think maybe he was as excited as the rest of them, and then when he looked for it and didn't see it in the CMB, that kind of burst his bubble a little bit. I don't know. Sorry, Oliver, if you're watching this, and it's a completely different story. The other sticking point, I think, the Hu et al. Analysis uses much finer binning, which I think, if it's real physics, is going to be more sensitive to that fundamental signal, and therefore because you've got more bins, you can kind of stack the signal more times over the noise. But also, if it's systematics, you're going to be amplifying that systematic error by having more fine binning. So that kind of goes both ways, that if it's systematics, you'd expect to erroneously see a bigger sigma, and if it's fundamental physics, you'd expect to see that more sensitively. But that might also explain why they got their different signal strength. But okay, this is a non-expert on the subject's paraphrasing of the panel discussion. I'll make sure that there's something popping up on the screen right now that people who want the experts' opinions, these two groups, you can go and watch that, and all the other videos from Parity Violation on the same YouTube channel.
Yeah, so that was our initial motivation to look into this parity violation. And we live in an era now where we have these large galaxy surveys, the current and the future galaxy surveys, such as DESI, Euclid, SKA, which are like probing larger and larger fractions of the sky. And this is the time when, if we want to measure higher order statistics, such as the trispectrum, we will be more likely to do it. And we're also probing onto scales, which are now much larger than the equality scales. So going towards the left-hand side of the graph. And that's one of the reasons why we looked into the trispectrum as well, because we will finally be able to measure it at some point, we hope.
There's no reason on the like technical calculational level why this needed to wait until now. It's just that it wasn't interesting enough to dive this deep into this.
No, so we've been doing sort of similar work, which I'll describe shortly. And it was only when we found out about this parity violation in the trispectrum that we realized that the things we've been working on, the relativistic effects in the bispectrum, would actually come through to the trispectrum and have the same parity violation.
And I guess the cool thing about this is that like relativistic effects are normally like some small addition to a largish signal, and it's very hard to extract it from other stuff. But I guess when you expect the signal to be zero, if you've got a very small non-zero relativistic effect, it's easier to tell that you've spotted it, I suppose. Awesome. Yeah, like as I said, parity violation is one of the most popular things on this channel. So getting into the motivation why maybe was less necessary for this than others, but you did a good job anyway. So everyone's hopefully very excited. Let's get into the details. What did you do in this paper? Why is there an effect in the standard model that should look like parity violation once we take into account redshift space distortions, and how does it come out of the maths?
Okay, so let me just begin with a bit of background. So we've been working on relativistic effects in the observed bispectrum for a while. And I can just explain why we get a parity violation in the observed signal, even if it's not there in the intrinsic distribution of galaxies. So we don't observe in real space as we would see in a simulation. We observe on our past light cone, so in redshift space, and it's well known that this produces a distortion. The most important of these is the sort of Kaiser effect, the redshift space distortion. So if we have a cluster, stuff falling into that cluster around it, in redshift space, a sphere will look like a slightly squashed ellipse on large scales within linear perturbation theory. So that effect, known as the Kaiser effect, produces a symmetric distortion where we have a sphere turning into an ellipse. So it has a symmetry about the line of sight still. If we reflect it, it retains its same symmetry. In sort of math speak, in Fourier space, we've got a line of sight vector n and a Fourier space vector k. And the dot product of those two things is the sort of angle that appears in the observed galaxy power spectrum shown here, where the intrinsic power spectrum P of k gets distorted by this factor, the bias plus the growth rate times mu squared. So being an even function of mu means that under a parity reflection, where k goes to minus k, mu goes to minus mu, but mu squared stays the same sign. So there's no parity breaking in such a term. The powers of mu determine whether the symmetry is broken when we include line of sight effects such as redshift space distortions. Of course, in the Newtonian picture, there is no asymmetry from looking in redshift space rather than real space. But when we include the relativistic terms, so the local relativistic terms coming mainly through a sort of Doppler effect at the observer, they're kind of part of the same signal, but they tend to be split up into these two separate effects based on when they were derived effectively. So MacDonald was the first to derive this, followed up by Yu and Bonventura, Challoner and Lewis a couple of years later, derived the corrections to the galaxy distribution in observed redshift space, with leading relativistic correction here shown in red, where we've got a v dot n correction. And that v dot n has an asymmetry in it. When we look in Fourier space, we have a single pair of mu, which changes sign under k goes to minus k, parity inversion type of thing. So that's a sort of the leading relativistic term in the density fluctuation. But when we go to the power spectrum calculated from that, it still remains parity invariant. So under mu goes to minus mu, we still have a power spectrum which stays the same. So the density field has this parity thingy, but the power spectrum that we observe remains parity invariant. Where we're leading to, I guess, is how to measure this. But actually, before we get to that, there is a way to detect this that people have been looking at using a multi-tracer method, where instead of looking at one type of galaxy, you take two and cross-correlate them, and that isolates this relativistic term. So it generates a dipole in this cross power spectrum. But that's not quite the same effect that we're talking about today. That's more of a way to try to measure these relativistic terms because it amplifies the signal in a power spectrum analysis. So if we move up from the power spectrum to the bispectrum, which is where we kind of came into this issue, instead of looking at pairs of galaxies and forming the power spectrum of the Fourier transform of those, we look at triples of galaxies, so the 3-point correlation function, Fourier transform it to get the bispectrum. So again, within the sort of real space distribution that you would get in a simulation, as Pritha described, we still wouldn't have a parity sensitive statistic, but once we observe on our past light cone with these relativistic subleading corrections to the sort of Kaiser redshift space distortions, we get a whole load of new contributions coming in. So these are the types of effects that appear where we've got we need to go to second order in the density perturbation as observed, and we get corrections to the Doppler term that we saw before. So we have an order 2 Doppler term, and then we've got cross terms between various contributions like the Doppler correction multiplied by density term, and density gradients come in, and transverse velocities and so on in quite a messy way. But the point, I guess, is that these terms now break the symmetry such that when we observe a triangle of k vectors with a radial direction vector n, the sort of parity invariance is broken because the triangle now has a handiness to it. Under a reflection, it is not the same.
Did Pritha not give an argument at the beginning about why just 3-point functions, just bispectra, you can't see it because you can essentially reflect it and rotate it, and it becomes what it once was? What is wrong with that argument in this context?
So I guess in a sort of fundamental sense, that once you observe in redshift space, you're no longer looking really at triangles because you've got an observer in the picture as well. So fundamentally, you've got a tetrahedron. So it's kind of like a trispectrum in some level, but with one point already fixed. That doesn't necessarily give you a parity violating way to measure stuff, and the Newtonian picture doesn't have this. It's always even pairs of mu. So your distortion in redshift space with the Newtonian corrections is always symmetric. It distorts into kind of ellipses at some level, whereas the relativistic terms are subleading to that, but the leading relativistic contribution distorts into kind of egg shapes rather than ellipses. And so you no longer have this symmetry along the line of sight.
Okay. Maybe you will get into this then at some point, but is there a really cool way to actually look for this in the bispectrum, and should we be worried that we haven't seen it if we want the trispectrum measurement to be explained by this?
Yeah, so there is a signal in the bispectrum, and its leading signal is in the dipole. So if you decompose in spherical harmonics about the line of sight, so not on our sphere, but about the line of sight, one can decompose that into spherical harmonic components, and it has a quadrupole is a standard way to look for the Kaiser redshift space distortion contribution, but it now has a dipole as well, and that dipole reflects this asymmetry and is kind of equivalent to a parity violation in the bispectrum. So a sort of smoking gun signature for these relativistic corrections lies in the dipole, and that dipole should be detectable with a Euclid type survey. So it requires that sort of volume in order to see it. So on equality scales, it becomes a sort of 10 to 50% correction to the monopole. But on smaller scales where the bispectrum is being measured, it's sort of subleading percent level correction, and nobody would have been able to see it yet. So that's a sort of motivation of why we thought there would be a parity violation in the trispectrum, which is where Pritha started calculating.
Yeah, it's the same idea of how the bispectrum was calculated, to do the same thing with the trispectrum. So instead of dealing with 3 galaxy number density counts, we now have 4 in Fourier space. So it's the standard way of setting up, where you have your 4 galaxy number density fluctuations, and you end up getting your trispectrum with your Dirac delta. So the Dirac delta just means that your quadrilateral, which is, so now in the case of trispectrum, it's going to be a quadrilateral in K space rather than a triangle. And this quadrilateral closes on itself. So K1 plus K2 plus K3 is equal to K4. And now the math gets very interesting. We have to expand the density field to third order, because even your tree level trispectrum, you can construct your tree level trispectrum with these terms. So you have your 1113 term with 4 permutations, and your 1122 term with 6 permutations. And this is your full tree level, the terms that contribute to the connected part of the trispectrum. This might be a way of looking at it, of the trispectrum in K space, where you have your 4 vectors joining up to give you a quadrilateral, and then you have that extra line of sight n, which comes into, or which takes into account these relativistic corrections. And you can also have it as the thing on the side, where you can see the different angles that you vary. So you have the picture where you have your 4K vectors in K space, your line of sight n going in a direction, and then the standard mechanism of setting it up with your different angles with the vectors. So just to reiterate on what Chris was saying about your about the powers of n in the number counts. So for the trispectrum, you need now your extra number count is your third order number counts. So we can break it down into very nicely into a Newtonian part, which is usually what's used in these approximations so far, and the relativistic part. So the Newtonian part has your third order density fluctuations and more terms with second order radial derivatives. But the leading relativistic contribution at third order is your massively long equation, but it now has your Doppler effect, which is asymmetric along your line of sight. So your Kaiser terms, which are encoded in the Newtonian part, is symmetric along your line of sight. But once you take into account these relativistic parts, which has the Doppler effect, more coupling terms, but your leading effect in your third order peculiar velocity ends up being the bit that gives rise to the odd parity part of your trispectrum. So if we look into it a bit more details, we can see that when you are doing this parity transformation, which is where your mu is going to minus mu, in K space, it ends up with mu as K dot n. So your mu going to minus mu will be invariant when you have even powers of n, but when you don't have even powers of n and have odd powers of n, it will end up giving you a signal. So if you're going from mu to minus mu, you will pick up terms which will not be the case in the Newtonian part. So if we can see all the terms in the Newtonian parts, they're all even powers of n. So if n goes to minus n, it doesn't make a difference. But your Doppler type relativistic effect are all odd powers of n, which is if your n goes to negative n, which is what happens in a parity transformation, you end up picking up a signal from your Doppler type relativistic effects.
I guess I have two questions at this point. I mean, is this again all kind of just coming from what Chris called the kind of egg effect, where in Newtonian things you just get an ellipse, and in this you get an egg, and okay, an egg, when you reflect an egg, it is no longer, it's an upside down egg, and this is just like that effect at higher and higher order?
Yes. So it's almost like when you're looking back in your light cone, the quadrilateral that you're observing is getting distorted. So this is not coming from an intrinsic parity violation, but it's more of the fact that you're observing back on your light cone. So there are effects like the peculiar velocity of the galaxies, gravitational distortion effects, which all come into play. So when you're looking back, it's stretching or distorting your quadrilateral in a sense.
And it would still be true that if you kind of did an analysis where you parity reversed everything by some plane that you put down in the universe, that you would still expect to get a zero signal. It's just that in this, you're kind of doing the reflection over different axes as you kind of rotate where you're looking at on the sky.
So I think an easier way to put it is, usually when you're looking at the observed trispectrum, there are two parts to it, right? So there's one which is the Newtonian or the Kaiser redshift space distortion that people usually look at, or people usually care about, which comes into your, so when Chris was saying, when we decompose things into the multipoles, when we have monopole, dipole, and so on and so forth, the monopole is usually what comprises of the Newtonian RSD contributions. So in your monopole, you wouldn't detect this effect because it's all even powers of n. But once you take into account these relativistic Doppler type corrections, which come into play in your dipole, you will end up getting quite a huge signal, and we'll see once I show you the plots.
And I think that the key part of what you just said that is important here is it's not the dipole thinking of like there being some big dipole on the sky, like the CMB dipole, but you mean the dipole at every single point in space. And as I rotate where I'm looking, the dipole is itself rotating. It's kind of the local dipole of the XYZ coordinate that is the important part here. Is that right?
Yeah, so you would extract your dipole about a line of sight. So if you take your trispectrum or bispectrum or whatever and basically integrate it over all lines of sight at that point in Fourier space, that would give you then your dipole. But you're right, it's not a dipole on the whole sky.
We were able to get the full trispectrum. This is just the trispectrum in terms of the kernels in Fourier space. And we broke the kernels down into two parts, which is your Newtonian part and the GR part. And your Newtonian part is what we don't expect to give rise to a parity contribution, but the relativistic part, or the Doppler type part, which we do expect for it to give rise to a parity contribution. We then defined the parity even and the parity odd part of the trispectrum. So when k goes to negative k, this is your parity conserving part. And if we took away the negative k from the positive k of the trispectrum, we end up getting your parity odd part. So if this signal is non-zero, that tells us that there should be a parity violation or a parity odd part of the trispectrum.
Cool. And at this point, if one wants to kind of verify your calculation, it's just, you just have to sit down and brute force calculate everything out? Or have you got like a Mathematica package or any other package that one can kind of simplify the process?
Yeah, basically everyone's on their own. We have to do it again. We are preparing a follow-up paper with more of the details.
It sounds like there might be a project for someone watching out there to build the relativistic redshift space distortions Mathematica package for the community.
Yes.
So we then plotted these two trispectrums, where we have the odd trispectrum in the dashed line and the even trispectrum with the solid lines along K. And this is for a particular geometric configuration. So what I was showing in the triangle picture with all the different angles, so you can fix that angle to give different geometric shapes of how your quadrilateral will look like. So this is for a particular shape. And as you can see, as you go beyond the scale, your odd part of the trispectrum actually takes over to the symmetric part of the trispectrum. So once you're going into much larger scales, this relativistic part of this Doppler contribution dominates over the Newtonian contribution. But even if you're looking just below equality scales, you still have like around a 10% contribution going on. But obviously, once you go much higher, larger scales, this contribution increases and the odd part dominates over the even part of the trispectrum.
If I might just interrupt with not a question, but this is making me remember another thing from this parity violation panel discussion between those two groups, that another thing that Oliver was skeptical about was that if the signal being seen in the parity odd trispectrum was real, most of the models that he thought were realistic that could produce this would have an equally large parity even primordial trispectrum, which hasn't been observed. So it was like, okay, what funky model is producing a larger parity odd one than parity even one? But okay, here you've got not even a model, right? Like this is the real universe. It might be that the amplitude is too small, but you've got a real universe where the parity odd thing on large scales is bigger than the parity even one by some large ratio. So that's very interesting to see. Yeah, again, not in some, you haven't cooked up some funny model. This is general relativity.
Yeah.
Mm-hmm.
This is another plot which is showing the ratio of the odd part of the trispectrum over the even part of the trispectrum with respect to the viewing angle theta on this axis and then k on the other axes. And this is also for a particular geometric shape, but this time we are also varying theta, which is one of the angles. So essentially we could, which is something that we will be looking into more, is changing the parameter space to optimize the signal of what largest signal you can get where this odd trispectrum or this odd part of the trispectrum dominates over the even part.
Yeah, so basically this is showing on large scales that the odd part is significant. The
Yes.
relativistic terms start to dominate above the equality scale.
Yeah, so persuade me why we haven't solved the mystery of what the Hu et al. Group saw. Like, why is it not this? Is this? Do you expect this amplitude is just too small that even though it dominates over the even one, it's still too small to have been what they saw? Or is the problem also that kind of what they did by like summing tetrahedra is such a kind of observationally natural thing, but theoretically very difficult to kind of model thing that you just don't know whether what they've seen could have accidentally been very sensitive to this signal. What is the answer?
So I think so what we have found wouldn't give you a parity violation in the monopole of the trispectrum. So once you integrate over all possible lines of sight for a given tetrahedron shape, that part of the signal will be zero. You'll have a dipole contribution, but not a monopole. So in theory, if you average over all tetrahedra in a evenly weighted way so that they've actually calculated the monopole, you wouldn't see this signal. It would get rid of it. So, I mean, there is a possibility that there's been, because they weren't expecting to see a parity violation in an odd multipole, it's possible, I wouldn't say plausible, but it's possible that there's some contamination from parity odd modes from odd multiples leaking into a monopole signal. If one's aware that it's there, then you'd be very careful to not let that happen. But with window functions involved and all this sort of thing.
Yeah, I was going to ask about window functions. Like, are they somehow blocking off certain tetrahedras at certain points of the sky because you've got a sort of patch where you didn't see things quite as well at some redshift or some angle?
Yeah, I'm not sure about that, but it does mix up multipoles at some level.
So if you're already aware of it, one would be more careful
to remove it.
To remove it and make sure that you're not observing. So it could almost be like a systematic where this information could leak into the monopole if you're not careful about making sure that this is there.
Yeah, I mean, systematic is one person's systematic is another person's signal. I guess I would call this a systematic 5 or 10 years from now when people are really trying to, extract the dipole and the monopole. But at the moment, if what they've detected is what you've seen, what you're talking about, leaking from the dipole into the monopole, that's a very interesting signal rather than systematic. I get what you actually meant.
Yeah, I mean, another way to look at it is people are trying quite hard to measure relativistic terms in the multi-tracer power spectrum, and presumably will do with the bispectrum. So here's another way that it appears. Is another way to frame this paper. So in fact, if these results hadn't been found and we'd bothered to do this calculation, which may have been would have been less likely to do, I think,
Yes.
without these sort of results or questions being around, it would have been framed as here's how to detect relativistic effects in the trispectrum if one was so inclined.
The other thing that maybe makes me think that indeed you're right, that this isn't likely to be what they saw, is that it would be unusual for it to be smaller in the trispectrum than the bispectrum. Or has no one looked for the equivalent of this in the bispectrum in just the right way that one would see it? Or is it, again, that the way that they looked is so opaque that it's kind of hard to know?
I wouldn't know the details of how they've looked enough to say, But as far as I know, nobody has tried to look for this signature in the bispectrum. And performing sort of, basic signal to noise calculations suggests that surveys done up to now, you wouldn't see it in the bispectrum. Looking for the dipole in the signature, you need something like Euclid, SK intensity mapping, that sort of scale of survey, in order to see it. Presumably that's the case in the trispectrum as well, although we haven't done a signal to noise calculation to see how big the signal is. If one was to try and measure it, it does look like it's quite a big signal from
Yes.
theoretical calculations, but that doesn't. But it's hard to say.
Yeah, yeah. Okay. And I guess that argument from first principles of why bispectra shouldn't have a parity violating signal. I mean, I'm just kind of speculating here. Even though you do now have the observer, so that's adding that fourth point, I guess, at the 4-point level, you don't need the observer to be adding a fourth point. So maybe there is an argument there as to why, even though the bispectrum might have a non-zero signal, the trispectrum would still have a bigger signal, I guess. But as I guess you were implying, one should look into the details to know the actual answers. Yeah, cool. That's very interesting, as one can see by the fact that I've been interrupting with the where to next already before formally introducing it. But let's get to where to next. And the first question I want to ask you guys before you talk about what you actually prepared is, if you had the Philcox and Hu et al. Groups with you, what would you tell them to do? Like, what? I guess there's two things that I feel like you might want to tell them to do. One is, as you were saying, if you expected this leakage from dipole to monopole, there'd be ways to try and remove it. How could they do that? From the theory perspective, I guess from the observer's perspective, maybe you don't know the fine details there. And the second thing is, yeah, if one was to go and look for this in either the bispectrum or a very sensitive way to look for it in the trispectrum or 4-point function, what would you tell people to do? And yeah, if people are watching, maybe go and do it. And it'll be very exciting if you see a boost in the signal or don't.
Yeah, in terms of if we were speaking to them, I'd just be curious as to whether they've calculated the monopole, which I'm sure they have, but whether there's any possibility that, whether there is a possibility of a leakage of this signal into the monopole. So if one was not expecting it to be there, one might perform the analysis in a different way than if you knew that there was this big signal that you needed to remove in order to look for a more fundamental parity violation.
If you thought leakage from dipole to monopole didn't matter because non-zero is still super interesting, you just do it. Whereas if you know that that's a risk, I see. Yeah.
If you know that you've got this signal that you have to remove in order to see a primordial parity violation, then it might be that you do the analysis a little bit differently. I don't know.
Anything else you would say to them?
The same thing, really. If you want to look at something which is intrinsic to the trispectrum itself, which would come into the monopole, because mathematically it shouldn't, as we've seen. So the fact that there is a signal there could be that it's leaking from a higher order multiple, which has a very high parity odd part to it.
I guess it doesn't even have to just be the dipole, right? I guess it could be any odd multipole that has leaked.
Exactly.
Mm-hmm.
Yeah.
That's right.
Yeah. But because the dipole is the leading order relativistic effect, it has the higher percentage, I'd assume.
Yep. So what else do you guys have planned next? You said you've got a more detailed analysis paper, but once that's out, where do you want to be taking this next?
So I think one of the things to do in this scenario would be to explore the parameter space a bit more. So we have the different angles that are contributing to the shape of the quadrilateral that we take into account when calculating the trispectrum. So there is a parity odd part for any geometrical shape that you take into account, but the way you look at geometrical shape almost dictates how much this parity odd part will be dominating at larger scales. So it would be a good way of actually seeing what the detectability of this odd part of the trispectrum would be by looking at different geometrical shapes and seeing how the physics of what's going on in the geometry works out to be. Yeah, that would be the next step that I'm working on, to see how this odd part actually changes with the geometry of the shape itself.
So one thing that strikes me as a very productive path to take, although it might be very difficult, is these groups estimate their uncertainty in multiple, or like their noise, sorry, in multiple ways. But one of the most sort of compelling is by performing their analysis on mock galaxy catalogs. Of course, those mock galaxy catalogs were constructed assuming Newtonian physics. I mean, I assume they were. The benefit of the mock catalog is, of course, that all of the kind of observational window functions and this and that are kind of meant to have been factored in. So if there is some leakage from dipole to monopole, that would happen. But of course, if the fundamental kind of model is not relativistic, then their mock catalogs won't have this effect. But yeah, is there some path to generating mock catalogs that would have this effect? For example, are there some of these groups are now doing kind of relativistic structure formation simulations? Would they, when then put into redshift space, see this, like this sort of Adamek et al. Field of simulating groups? Would they have a means by which to make mock catalogs that have this effect?
Yeah, so we've been looking into this. So there's a number of us who've been interested in trying to measure in the bispectrum to measure the dipole in simulations. And in fact, another PhD student, Chris Addis, has been investigating this for the bispectrum and is going to attempt to have a go with some of Julian Adamek's simulations that he ran while he was at Queen Mary. And so, like, yeah, it's sort of underway. It's a bit messy to do, but yeah, that's the sort of next step in all of this stuff to sort of because Julian Adamek simulations are sort of real GR simulations with full ray tracing and everything in there. It's a way of checking the sort of perturbative calculations are giving the correct answer at some level, and what we expect. So that's the kind of the next step, and then I guess if someone's brave enough to try that on the trispectrum as well, that could be sort of something that's interesting to do.
Yeah, but I guess if you did it but didn't take into account observational effects, you'd get exactly what you're saying, which is that the monopole shouldn't have a signal.
Yeah, that's right. Yeah.
Kind of need all of the above in one mock catalog.
Yeah, I don't know enough details about how you would go about doing that, but that would be a kind of next step.
And you said, I think, during the main content of the talk that a Euclid-like experiment should see this, but were you referring to the bispectrum at that point? Or because I guess you haven't done the kind of signal to noise estimates of this.
Yeah, so the bispectrum, we've done actual signal to noise calculations and some forecasting and stuff to show what should be detectable with the Euclid-like survey and future intensity mapping surveys from the SKA. And yeah, it should be a strong enough signal to detect quite clearly with Euclid. We haven't obviously done that for the trispectrum yet, but I would anticipate if somebody does it, then it would be a similar kind of signal.
Yes.
So that's another thing pointing against this being the signal that they've found, is that probably this is too small a signal for it to have been seen so far, but it's not obvious. I don't think that's the case.
Right. Unless there is some reason why the trispectrum might be bigger than the bispectrum.
Is it enhanced? Yeah.
Oh, yeah. So I have a super naive question then at this point. You say Euclid-like or SKA-like. What is special about Euclid and SKA that say DESI, which I guess is actually going to have public data in a matter of months, I hope, where months might be 10 to 12, I don't know. But
so it's just much bigger volumes, basically.
Okay. Because you need the larger scales, is that the...
Yeah, that's right. Yeah, so you need some kind of very long wavelength modes in order to see this.
Yes.
So it scales like they scale like h over k compared to the Newtonian terms, which don't have a k dependence relative to the in the RSD in the redshift space contributions. So they scale like h over k. So they're somewhere between picking up primordial non-Gaussianity, which goes like h over k squared. It's a stronger signal than that, but it's still weaker than the kind of dominant effect.
So follow-up naive question then. The reason why Euclid and SKA can see larger scales is, first of all, Euclid's in space, so it's seeing the whole sky. Is that part of it? Or is it also seeing deeper? And I guess SKA is certainly seeing deeper because it's at different frequencies. Is that the kind of point?
Yeah, so they just see to higher redshift, basically. So DESI might be able to see it, but again, sort of our signal to noise calculation suggested it would just be just about be detectable with DESI. Yeah, maybe they'll try to measure it. I'm not sure, but definitely Euclid should be able to see it.
What about the CMB? Because the CMB is very large scales and it's very, very well measured. Is there any prospect of seeing this in CMB trispectra or bispectra?
It's purely for sort of galaxy surveys, this effect.
It's the redshift space distortion stuff.
It's a single sphere, but they take into account all of these effects in their analysis. It's kind of fully relativistic, if you like, because they're used to looking at super Hubble scales. It's never been a question of doing a kind of Newtonian plus corrections analysis. It's always been a fully relativistic thing. Whereas with galaxy surveys, because most of them have been quite small scale, people have just done a Newtonian sort of analysis. But once you approach Hubble scales, you need to have a more relativistic perspective on it.
I guess also because the CMB is so much more, the density fluctuations on all scales are so much smaller. The relativistic calculation was a lot easier in the first place, I guess.
Yes, that's right. Yeah.
Thanks for that. That's super interesting, and I'm very fascinated to see, those follow-ups and whether one expects to see the trispectrum, whether one can make mock galaxy catalogs, all that stuff. Seems like very exciting and fruitful areas of research. So not just your group, but anyone watching it, I'm keen to see where it goes. Just the last question before we wrap up. What work being done in cosmology at the moment do you think is particularly interesting but underappreciated by the community?
Observing such large scales is giving sort of new opportunities to see new effects that we wouldn't see otherwise. So I think those are kind of exciting and ongoing, but it's not exactly underappreciated since everybody knows what's happening.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos, and click a like to help with YouTube algorithms, both for you and the channel, because your benefit as YouTube will know to recommend more stuff like this to you and share the channel with colleagues. If you have any questions or suggestions, leave a comment. Otherwise, check out, there's a video on this channel by that Huatao group who measured this 7 sigma signal of something, parity violation-ish, systematics, new old physics or new physics, and maybe also this panel discussion between the two groups who made that measurement with varying amounts of sigma. Other than that, thanks Pritha and Chris for the great talk.
Thank you.